And we're back. Steve Mildenhall working through his Python package called aggregate. So we'll put a link up to part 1 of this series, which walks through the first kind of third or so of this Colab notebook that we also have a link up to. What we're going to start with today in this part is reinstall the package, and then we will skip back down to where we left off last time. Okay, Steve, so I'm just going to install this, right?
Yes. And we should mention here, if you've installed this on your own machine, you don't need to reinstall it every time you run it. It's a one-time thing. This is just, it's not part of the standard Colab installation, so you do need to do it here in this case.
Yeah, and then, I mean, always love plugging Colab. Just such an incredible tool. I mean, just get free compute. Super amazing.
You'll notice from, I think last time we used about 0.11.3. This is now 0.11.6. And based on the conversation we had last time, I decided not to call it 1.0 because you pointed out there was really no point in doing that. So it's still 0.11.6.
How long did it take you, Steve? Like how much? I mean, you just released another point version. How much time do you spend on this thing? It really is awesome.
I think there's about 250 commits in my GitHub on it, and it's been sporadic. But I've been working on it. The repo started in 2018, and I've been working on it a little bit by then. So there's a lot of hours of
And is every commit incrementing a dot version number for you?
No. I've sort of got a little more rigorous about that process recently. So, and then just to remind folks here, so we're importing the library, and then from aggregate, you want to import build and QD. Those are sort of the two things that give you access to a lot of functionality. Build is an underwriter object, and it lets you create things using the deck language. And if we go down to our example 3 here, and the insurance commercial auto risk example, let's just build this guy. So just to remind folks, we looked at this last time. It's a little portfolio of about 500 units, 500,000 of commercial auto, comprising 10 claims. You've got a $10 million policy limit, log normal severity with a mean of 50 and a CV of 4. And that little block of code there at the bottom, you remember, is our statistics. It's showing that we're matching the mean, the CV, and the skewness of both the frequency and the severity pretty tightly. And it runs some validations, and it's coming up as not unreasonable, which is the highest level of confidence you can have in a model here.
And in the podcast. And so we will teleport ourselves down the notebook to straight away starting to price with this little portfolio that we've built.
Yeah. So I think we covered this last time, but probably good just to refresh. There's a lot of things here. So these distortion functions, if you just execute that guy, there's a list in that little table there of my usual suspect distortions, right? The constant cost of capital distortion, the proportional hazard, the Wang, the Joule, and the TVaR. They all look something like this. They're all functions that take a number between 0 and 1, and they map it to another number between 0 and 1. They take 0 to 0, 1 to 1. They're increasing, and they're concave, right? So they all look something like the orange line that you've got here. And the interpretation here is that if you look sort of at, say, the value of, you always call them G. I don't know, for whatever reason, distortion functions are always called G. G of 0.2 would be kind of the price that you would quote on a binary risk with a 0.2 chance of having a loss of 1 and a 0.8 chance of a loss of 0. So it's like a Bernoulli 0-1 risk. And you can see it's, in this case, it's, I can't eyeball that, it's about what, sort of 0.35, right? So it's giving you the markup that you would have on that risk.
I'll make a couple points. One of them is I just X'd away this thing saying your session crashed. That's a deliberate thing, and that allows us to reset the version of matplotlib we're using. So just in case somebody who's not used Colab before, you see a crash, probably freaking out, there's actually a function at the top there, which Steve put into this notebook, which forces your session to crash so they can reload something, just a technical detail. The other thing I wanted to say here on these pricing functions, I don't know that I mentioned this last time we spoke, so it's a good thing we're hitting this again. In my day, the thing that we had a few back-of-the-envelope pricing algorithms we would apply. So something like Sharpe ratio, right? Would that be an equivalent operation to what we're doing with these transformations? Or it's a pricing system, right?
It's a pricing system, right? All of these rules are, you plug in a distribution function and you get out a price. That's kind of what we're shooting for, and that would be one. You from the distribution function, you compute the standard deviation, you get the price. This is kind of another one, and we'll get to how you go from the simple pricing a simple risk to pricing complicated risk. We'll go through that as we move down here.
You also have these heuristics of EL multiples, right? Which are implicitly perhaps using some distortion function, right? But you sort of have these, they're market-driven results, right? And that would, again, I'm trying to map this over because I never used this stuff when I was pricing reinsurance business. We would use these other, probably less, certainly less technically coherent and small c sort of frame. Do you have any other comments to make on that, Steve?
Well, actually, if you let's go down, because I think we're going to get to let's just import this guy and run this. So aggregate extensions is a sort of submodule of aggregate that contains development stuff and things that are it's not like part of the main package, but it's got in it some of the figures from the book Pricing Insurance Risk.
Yeah, nice.
And this one I think is quite a helpful one to look at. So this is figure 10 points. It's chapter 10, figure 3 in the book. And we're showing that same distortion that we just plotted above. And we're sort of highlighting, the meaning of the different values, right? So the diagonal line that you've got there, the blue line, that is that corresponds to the loss cost, right? Because it's the y equals x line. So if you've got your Bernoulli risk, and the vertical line is at 0.3 in this case. So the loss cost is 0.3. That's the blue dotted line. And then the premium that you charge for that risk would be G of S. So that's about a half, right? And so the orange dotted line, that's your margin that you would have in the premium. And then we're always thinking that this has to be written as a sort of collateralized layer of $1. So the amount of capital you would need would be 1 minus the premium. So that would be the green bar, right? That would be the amount of capital that you've got there. And you can see sort of from those three things, for this simple risk, you can recreate all of the metrics you were talking about. You've got your loss ratio, you've got your margin, you've got your return on capital, you've got your leverage ratio. And you could, if you've got loss ratio, you've got multiple, you could reciprocate it. So you've got all of those statistics here for a little layer. And then the trick is that what we can do with these spectral risk measures is you decompose a more complicated risk into a bunch of components like this and add them up, right? So as long as you can sort of price by individual layers, you can get all your statistics, you just add up some of the premiums, some of the losses and what have you, and you get a view for a more complicated.
So in my world that I was mentioning earlier, so the premium is the orange line, G of S, right? Mm-hmm. And in the world that I was living in and malpracticing from a technical standpoint, this margin calculation here, some EL multiple, if you're doing a rate online kind of exercise in the cat business, that's just a different heuristics for calculating this area, right, or rather this line. And so just to kind of emphasize one other point is the capital goes up to the top because this is $1 of limit, right? And so up here, there's $1 expected loss every year, and so there's $1 limit, and so you have to have the capital to fund the loss, even though there's a 1% chance of loss. The loss is still $1, so it's got to come from somewhere, and it comes from capital, which gets shared amongst other things, and we will come to that, no doubt.
Yeah. Mm-hmm.
Okay, great.
All right, so let us try and price our that commercial auto policy that we set up, the A object. Let's price that. To do the pricing, you need to give two variables. You need to say how much assets you're going to support the risk with, and you need to give a distortion, right? That's going to adjust the probability. So what we've executed here, A is the object we created for the commercial auto. The 0.99 refers to the capital level, and what we're saying is we want to support this risk with 99 percentile assets, really. There's no there's a bit of a blurred distinction between assets and capital, but so we're sort of having assets that are going to be adequate 99% of the time, and then we pass D in, and this will return for us this little data frame that's got 8 statistics, which I encourage everybody to look at sort of in all pricing situations. So L is the expected loss, 482. P is, and that notice that's slightly less than we had as the unlimited loss on this risk, right? It was 490 something because we've only got the 99% capital, so there's going to be a little bit of a haircut there.
This is an aggregate 99%?
Aggregate 99%.
Yep. Good.
I mean, you could argue here, actually, so I hadn't thought about this, but we're writing a $10 million policy limit here, and we've only going to support this with 2745 of assets, so, maybe there's a little bit of cut and fast and loose, right? But maybe should have thought about that.
Fair.
Not a wholly credible $10 million policy limit. Anyway, so a little bit of a haircut on the losses, bringing it down to 482. The implied premium, and we'll get to exactly how we're computing that, is 687. The difference between the premium and the loss is the margin, 206. Q is so A is our assets. The 2745 is the 99th percentile of our aggregate distribution for the policy. The Q is the capital, is the difference between A and the premium, all right? Because all of your assets, they either come from capital or they come from premiums. The only two sources that you've got in this sort of simple model. And then loss ratio, we know, loss over premium. P to Q is our premium to surplus ratio. So you can see that this is sort of an unrealistic portfolio in the sense that it's written at 0.3 to 1, right? So maybe
what does the M signify here?
Yes, sorry. It's milli, right? So it's engineering format. So K is thousandths, M is like millimeters. So 300 is 0.3. I'm sorry, I forgot that it did that automatically on here. I kind of like that formatting, but so that's 0.3 premium to surplus. And then your ROE is 1,000 mil, so 10%, right? 10% ROE, 100 mil, sorry.
10%, okay.
Yeah.
So
it's a reasonable ROE, but it's a pretty low loss ratio because there's no expenses here, right? So a 70 loss ratio is pretty low, but it's extremely low leverage. So you've got that usual triangulation between margin, return, and leverage.
So K would be killi as well, right?
Kilo,
so this is
thousands.
Kilo.
Yep.
Thousand. So it's kilo.
Yeah.
And this is milli as opposed to other direction.
And then I like it because it makes it easy to see the size once you get your head around it, because you have big M is millions, big G is billions, and then you get a mu for a millionths is sort of nice. All the numbers are the same width, but you can see the size. I'm imagining an infographic here, Steve. Maybe you could pop out here. Maybe you could create something that would help people with this, memorize this, because if it's unfamiliar, how every time you get a new textbook, you get a new set of notation. And, nice to see you're carrying that tradition on, Steve. Okay. Sorry about that. Okay. You can also price from the distortion by just giving it the probabilities. And you can see you got the same number there, right? The 687.74549 is the same as the 687.755. And then you're giving it the assets explicitly as the second argument.
I have a question, actually, and I meant to ask this before. The 99. So pricing to the 99, this is a price adequacy number, right? So this is saying I'm going to cover the scenarios up to like some kind of aggregate VAR thing here, right? So you don't want to include everything. Is this because this is the limit to the aggregate limit to the policy? Is that the idea here, or is there some other logic here?
Well, it turns out to be the aggregate limit to the policy because that's all the assets that you've got, right?
Yeah, right.
So
right.
It's just a nice round number, really. No one would ever price to just 99. If you look at where insurance companies run, they typically are running much more conservative capital levels than that relative to model. I mean, I know it's relative to reality, but the way you tend to model it out, it's common to see sort of a few basis point probability of default, not a 100 basis point probability of default.
Right. So this is useful. So different from a reinsurance layer, which will have a limit written into it, right?
Yeah.
This is a choice, which is subject to all the vagaries of how we choose how much to capitalize insurance companies. You're given this number and saying we're gonna capitalize the 99th, and that's gonna allows us to do all this.
Yeah, and it's generally companies manage it through, they'll have a rating, which broadly corresponds to a bond rating. You can look up then the default rates for corporate bonds of the similar rating and so forth. So it's a bit of a squishy thing, but you need to, at the end of the day, you need some level of assets that you're going to put into this to price. And I just chose 99 because it's a nice round number.
And when you say assets, that includes capital plus premium, right?
Yes.
Margin. So
Yes.
I think that's a distinction. I'm not sure you said it in this session. We did, I think, in the last one, but that's why the word assets is a good word to use there. Okay. Remind me what we did here again.
All right. So this second one is just showing you can also, so the first one we used the aggregate object and we passed in a distortion and we got the price. You can also use the distortion directly and just give it a vector of probabilities and outcomes and an asset level, and it will do the same calculation. So it's just an alternative way of doing the same thing. So that first thing, so remember the density DF is a pandas data frame that contains all of the information about the discretized probability distribution. It's indexed by the loss outcome and the probabilities. So that first thing gives us the loss outcomes and the probabilities. And then the second argument is just giving us again the capital level, 99% capital level.
I see. Okay. And because the density DF, the DF here means data frame, right?
Data frame, yep.
And then P total is what does that refer to?
It's a column, so it's one of the columns in the data frame,
right?
And it's the probability mass function of our approximation to the aggregate distribution.
Okay. Yes. And is this the stuff way back up here that when we built the thing that we created?
Yeah. It's right. It's what underlies the aggregate row of this table, right? So the sum product of all those probabilities and all those outcomes will give you 498. And the sum product of the squares, minus the mean will give you the variance and all that sort of stuff.
Okay. Okay, good.
All right. Okay. So what do we do to get the price, right? What's the approach, okay? And what the idea is that we're going to go back to our distortion function and we're going to apply it to the survival function of the distribution, right? So if you've got your survival function, remember, so that starts at 1 and it goes down to 0. It's the probability you have a loss greater than a certain threshold. And then we're going to apply G to that. And what that's going to do, remember, G is that curving up function. Is increasing and it lies above the diagonal. So it's always going to it's always going to increase all of the probabilities, okay? So when we get to G of S, that's going to have a kind of thicker tail. It's going to look pretty much like the survival function. It's going to come down and have a thicker tail. And then there's sort of a couple of ways you can proceed from there. The simplest to think of is, all right, so I've got my individual probabilities, my P total that I start with. From that, I can build my survival function. If you go up to the text here, we have an algorithm for doing this in the book. Okay, so where our inputs are, we've got this discrete distribution. It's got a load of outcomes xj and probabilities pj. So that's exactly what's in that density.df.ptotal data frame, right? That's the x's and the p's. Okay, yep. And then rho g is our curvy line. Okay. G is our curvy line. Yep. And then what we do is essentially the first three steps here you can kind of ignore because in this case we've got distinct outcomes. So you don't have to do any grouping or anything. Okay. What we're going to do is we're going to start with step 4 and we're going to decumulate the probabilities to determine the survival function. So we're going to say the chances that you're strictly greater than 0 is 1 minus the chance that you're 0. So that'll give us S0. And then the chances that you're greater than the next level, you just keep subtracting the p's that you've got, right? So you've got this column of probabilities, and you're sort of subtracting them all from 1. That gives you your survival function. So that's step 4. Then in step 5, you apply G to that. So now I've got this distorted survival function, and all of those survivals are all slightly bigger, okay? And then I sort of do the opposite of 4 to go back to probabilities. So I take the differences of those G of S's, and it's a backward difference because it's a decreasing function. So that will give me a whole bunch of new probabilities, risk-adjusted probabilities, that will be higher for the worst outcomes and lower for the best outcomes. Okay, right. And then I just take expected values with respect to that set of adjusted probabilities. That's all we're doing here. And that's the joy of that is you can allocate with that, right? Because if you've got probabilities, it gives you additive decomposition of expected values.
So there isn't a way to just take probabilities and distort them directly?
Well, this is pretty direct.
Because I think
I
of
mean-
like probability here of 0.2, and we apply our distortion function, now it's 0.4, right, or
Yeah.
whatever it is, right? But then, to have to go through this survival function, decumulate, it just seems to me like a lot of steps. Is there a reason why?
Yeah, so you could come up with a function that you would multiply each one by,
Yeah.
but kind of the way you do it is you would do all this stuff and you take the ratio and then you say, oh, I can multiply by that ratio. So it really wouldn't sort of win you anything. Adjusting probabilities is a little bit of a subtle thing. Because,
Yeah, that's what I was figuring, yeah.
Yeah, you need to make sure that they continue to add up to 1 and they're all positive and all this sort of stuff. So this is an easy way of doing that.
Yeah, interesting. And what's great about this is, although that is complicated, I really like your answer. The alternative methods, like the old things I used to do as a not very good actuary, just aren't they might give you an answer that allow you to say something reasonable about what the price of the risk is, but they're not. There are holes in it, right? There are problems technically with it. Doesn't add up to 1. These sorts of things, and that might not matter so much for the the wheeler dealer reinsurance pricing actuary, reinsurance broker pricing actuary. It matters to do more complex things later on when you want to allocate capital, and there's consequences to these technical shortcuts you might make. So I just want to.
Yeah, this is a nice way of getting a set of probabilities, and that will be consistent. It'll have nice properties. It'll be sub-additive. You won't be able to create weird arbitrages by combining different pieces of different layers and stuff. So it's a sort of solid set of probabilities.
Yeah.
So
awesome.
This little block of code just does what that algorithm says in pure Python by hand. Okay. So row 2 just extracts from density df the loss, the p total, and the s. S is actually, so that's your survival function. That's already computed, so we don't need to do that again. Row 3 just applies the g function to s, right? So that's computing g of s.
What is bit.s? The
bit. I've made this. It's the. So I use bit as a variable when I take a bit out of a data frame. So
yeah, okay.
We're taking the loss column, the p total column, and the s column out of density df, right?
Sure.
We're putting them in this variable bit. We're applying g to s to make a new column called g of s. That's row 3.
Yeah.
Right. And then in row 4, we're only interested in kind of what happens up to the 99th percentile level. So we actually truncate the data frame at the 99th probability level of the aggregate outcome. And then in step 6, we do the differencing to get back to our risk-adjusted probabilities. So if you fancy doing some typing live, if you were to we've executed that, right? So if you create a new cell,
right,
somewhere down above or below, wherever you want.
I've forgotten the hotkey. You remember it, don't you?
Control MA or Control MB
B.
will give you one above or below.
Oh no, it activated something else. That's and during the live recording session, I know those hotkeys that are sensitive to all sorts of things. So I'm going to be careful here.
Okay, all right.
Where is there's this is move and there's insert cell here.
Oh, there you go. Code, the plus code. Yeah.
Boom.
Okay. The big plus. Yeah, there we go. Okay. So let's do bit, and then double open square brackets.
2 squares. Okay.
Yeah, and then do quote p underscore total, and then comma quote GP.
With that. Just
yeah,
lower.
and then go to the end, and let's look at that to just see if that looks reasonable. See what that is. It should be indexed by loss. Yeah, there we go. It's indexed by loss, and it's the 2 different probabilities. And to look at that, just hit dot plot on the end, and we'll get a little plot of that. And it might not. It'll probably.
Ooh,
yeah. Okay, that's sort of a bit boring. Let's put in there in the argument. Put in log y equals true. So we'll sort of see a bit more what's going on.
Does Python capitalize or not?
It does. Yeah, capital T. Yeah. There we go.
Oh, no.
Okay. So that now we sort of see what's going on, right? So we see that the orange is our risk-adjusted probabilities. The spike at the end, we didn't put in the P, so ignore the spike at the end. That's a slightly different feature. But what you're seeing is that from about, 400 and up, the probabilities have all increased. And below 400, the probabilities are all quite a lot less. And that's your adjustment. That's your set of risk-adjusted probabilities.
Right. I see. So we're saying when you said above or below, that's like blue is above the orange line here, and then it crosses down below. Right.
Yep, exactly.
P total is the original, and so again, the orange line, nice, that's consistent, is the adjusted revolution. Okay. And what happens out here?
Okay, so what's going on there is to compute this expected, all of the states 99th percentile and above all get collapsed down into the 99th percentile outcome. So we've got to add up all of that probability. We did that quite carefully for the GP row, but we didn't do it for the P total row. So it's just not there. But we don't use that in the calculation, so it's okay.
Right. It's not relevant for pricing, the original. Yes.
Well, it's not relevant for what we showed here.
We're not really. Yeah, right. Not relevant.
Yeah, you're picking up your probability of a limit loss there, basically.
Yeah, right. Thank you for saying that. Good. Yes.
All right. Okay. So what? Let's. Oh dear. That's okay. Forget that. Yeah, we don't need to do that. Let's skip that. So that's a quick reminder about distortions.
Yeah, we've already done all that.
we looked at one type of distortion there. We applied it to an aggregate distribution. We showed how it produced a higher premium. So what we want to do now, this is really the beginning, I guess, of today's session, is I want to look at portfolios, and we're going to look at this sort of, I call it the classic cat non-cat example. And I'm sure, David, you've also seen with clients, people struggle with how much cat risk to write because it's just different, right? It can really spoil your day. You can have these big losses. Yeah. It's just very, very different. And so this is a little portfolio. So up to now, we've been considering one line at a time. Now we're going to combine two lines, one called cat and one called non-cat. And we're going to make those into a portfolio so we can add them up. And you can see that the syntax for the ag cat, that kind of looks like our commercial auto, right? So cat is the name, it's an aggregate, it's got 1.8 claims, it's 100,000 x is 0. The severity is a Pareto with an alpha of 1.8, so it's very thick-tailed. It doesn't have a variance, it just has a mean, and the lambda parameter is 1,000. And then the non-cat line is a lot more of that. There's 15,000 of loss. It's 1,000 x is 0, so like $1 million policy limit, and it's the same severity curve, log normal with a CV of 4 that we used. And then it's got a mixed gamma frequency, meaning it's a negative binomial frequency with some sort of uncertainty about the parameters there. So those are kind of two things like the commercial auto that we had before, and it's going to add those up to the total, which will be this portfolio. CNC stands for cat non-cat.
So this is this in fact? I mean, I guess the terminology you're using here suggests to me this is actually two portfolios, a cat and a non-cat portfolio.
Yeah, I call them units. So it's sort of John and I struggled when we were writing the book. What should we, because is it geography, line of business, business unit, what is it? Yeah. And we came up with the idea of calling them units as a generic catch-all for whatever division you want, right? So it could be, so we're thinking here that there's a portfolio which could be a whole, typically we're thinking of this as sort of the whole company, and it writes two things. It writes some cat business in the cat unit, and it writes some non-cat business in the non-cat unit.
Okay.
Those are the two pieces.
So they're failing validation, Steve.
So let's look at that. So the next block for cat and non-cat, those are aggregate objects. So they're the same as the commercial auto object we had before. And so these blocks of 3 lines are the exact same thing that we had before. If we created cat on its own, its validation would look like this, right? And the non-cat would look like here. And then the total is just adding the 2 up, okay? And they're added up as though they're independent, which in this case for cat and non-cat is probably not an unreasonable assumption to make.
Yep.
And just to remind folks here, the key thing we're looking at is we want the E of X that's like theoretically what we would expect the answer to be for the mean. The estimated is what aggregate's computing with its little algorithm, and the error is the relative error between the two. So cat is doing pretty well on 10 to the minus 7 for the severity, 10 to the minus 5 for the aggregate. That's sort of indicating that there's not quite enough space, because there's no reason why those two errors should be different like that. It's what 2 orders of magnitude higher on the aggregate, so we don't like that. And then on the non-cat line, those errors are just too big, right? I'm shooting to have an error of less than 10 to the minus 4, so I don't like, that's 2 times 10 to the minus 4, so that's no good. Okay. So that's why it's failing validation.
Right, but every single one's only aggregate.
Yeah, this is the aggregate object reports when things fail.
Oh, I see. That's your aggregate object. Okay, so cat fails, non-cat fails, cat fails.
I don't know why it's reporting it twice, but it's really insistent.
Yeah, it really doesn't like it. Now, it would seem to me, though, that on the cat, this you said 10 to the minus 4 is your heuristic. This should pass on its own?
So it's got a number of tests that it looks at, and one of the tests is it wants the aggregate error to not be too much bigger than the severity error, because I don't know if you remember, but there's this thing called aliasing that happens with the FFT routine that we use here. You get this problem that large claims wrap around and they reappear as small claims.
Yeah.
And a sign that that's happening is if the aggregate error is bigger than the severity error, then that's a sign you've got aliasing. And that's a sign that you don't have enough space for the answer. There's not kind of enough, you can't get to large enough losses with the discretized parameters that you've chosen.
Interesting. And that's a reference to kind of fast Fourier kind of terminology, the aliasing, when you're wrapping around. It's like the function goes over the top and comes back on the bottom. We did get into a discussion on LinkedIn briefly. You did with one of your commenters about aliasing, so it was nice to see that reference. Yeah. Okay, so what do we do?
All right, so what we do, we've got two different things going on here. The cat is saying essentially that there's not enough space, and we can solve that either by making each bucket bigger or having more buckets, okay? Yep. The non-cat one, that severity error there, that's actually saying the buckets are too big, okay? And it wants smaller buckets. And you often have this tension between bigger buckets, smaller buckets. So what we need to do is we need to make the buckets smaller, and we need to have more buckets, and we need the end total that if you take the number of buckets times the bucket size, that number needs to get bigger, right? So I think if you go down, at the moment we're using log 2 is 16 and bucket size is 2. So let's update it with log 2 is 18. That's 4 times as many buckets, right? Because it's 2 to the 16 is 64,000. 2 to the 18 is 256,000. And a bucket size of 1. So we've 4 times the number of buckets, half the bucket size. So we've got twice as much space as we had before. And bingo. Now everything is not unreasonable. Okay.
Great. So and we lose the warnings. And then we, wonderful. Yeah. Okay. Good.
All right. So now we're going to set up a pricing framework. And I should say here, what I'm trying to explain with this stuff is not that this is necessarily how you should price, but that I want to enable people to understand what they should expect the methods to produce. Okay, so it's building your intuition for how these things are going to price. Mm-hmm. And so you need to have some sort of baseline that you're going to use that you can consistently compare across methods. Because there's just too many parameters here, right? So we need to nail a few things down, and then we're going to apply a bunch of methods that we believe are broadly consistent, and we can look and see what are the differences in results. And the differences we're going to be looking for is how expensive do they think cat is versus non-cat, right? That's the key difference that we're going to try and look at.
Okay, they here being the result of the assumptions we're making. Is that
right? The different pricing methods that we're going to apply. Okay. Okay. So what we're going to do is CEOs love to, we're going to make a 15% return across the cycle, and we're going to hold capital to some level, right? In Europe here, they often talk in terms of multiples of Solvency II capital, whatever it is. So the CEO of this little company has decided he or she wants to achieve a 15% return over the cycle, and they're going to hold capital to the 200-year event, so which is the Solvency II standard. Okay?
Okay.
So what we need to do now is we need to parameterize a bunch of these distortions to match those goals and objectives, right? In total, they're going to price to that level. So P-reg is going to be our regulatory capital standard as a probability. So that's, yep, you nailed it. The 99.5 is 1 over 200. And then we'll compute our assets A as the 99.5 value at risk in aggregate from our portfolio. So if you execute that, you get, that's the 44,495. Okay, so that is your 1 in 200 return from that book that we created.
P.Q. On that?
So P is our portfolio. The portfolio object was called P. Maybe we should have called it port to be a little more descriptive, but that's the guy we made up there.
Yeah.
that guy. Yep, row 1 there.
Yeah.
Okay, and then Q is the quantile function, so it's another name for it's the inverse of the distribution value at risk function, and you pass in 99.5, and it pops out 44,495. Okay, so that's our asset. That's how much assets we've got, and then nice round numbers. What? I guess I'm not, sorry, I am not pricing to a 15% return here, am I? I'm going to price to a lower return because sorry about this. I'm going to price to a $20,000 premium, right? That's what the market rate for this is. So let's back into what return can we get with the capital standard we've got with a 20,000 unit premium. So the premium is 20,000. The expected loss is then going to be the limited expected value of losses from our portfolio at our capital standard, right? So that's going to be the EL there. So density DF has got a column called LEV total, which gives you the limited expected values, right? So that allows us to get to the LEV.
And we calibrate that here, right? So that's what we're saying.
Right,
11.5
that's the capital there. Yep.
That's the most we can use.
Yep. Okay. And then the margin is going to be the premium minus the EL. And then the ROE or the COC stands for cost of capital. So that's the margin over the capital. Capital is going to be the assets minus the premium. Okay. And then V and D are just the discount rate and rate of discount. And then we run that and we see 11.8% cost of capital. And there's a little bit of schizophrenia here. One of the things that became apparent to us as we wrote the book was that really getting to grips with this difference between equity and capital. And most of the time we actually sort of want to talk about capital and cost of capital, return on capital, not equity, because equity includes other things. But so I try and
give me an example of something else. Is equity an accounting value, do you mean, or?
Well, okay, so equity is the owner's residual value. Capital in this context is the amount of free assets from a policyholder's perspective. So the big difference is if you raise debt that is subordinate to policyholders, it increases capital, but it doesn't increase equity. That's the big difference.
Yep.
Okay.
Totally get it.
Yep.
Okay, let's do this cell. And I have a question going back here, but I want to know what this is first.
So this is just our expected policyholder deficit. So because our EL is with losses limited at our 99.5 capital, PS is our actual mean losses. The difference is a 0.6 of a percentage point haircut because we've got limited assets.
Right. So I see. This is the consequence of the 99.5.
Yes.
Yeah.
Yeah.
Right. Okay. Cool. Now, so I recognize maybe we had to do a little bit of footwork here to go from the return on capital, what's the premium, to the premium, what's the return on capital, right?
Yes.
Now, how hard would this be to rewrite to reverse the flow here?
Oh, it's easy. We would you would take row 4 and you would solve it for premium.
Okay.
So
I see.
Yeah.
Right.
You
just do the arithmetic to pull that, or the algebra rather.
The formula would be that it would be the EL plus the ROE times the assets divided by 1 plus the ROE. That's the formula that would give you.
Prem 2 equals.
Yeah. Prem.
EL.
So do open parens, EL plus, and then if you want to do it to 0.15, or do you want to confirm what we've got here?
Let's do 0.15.
Okay, so do 0.15 times A.
Did we write that down up here? No, we didn't yet. Okay.
No, we haven't yet. So times our assets A, and then all of that outside the parens divide by 1.15.
And that is the 1.15. Okay, that's the same as this.
Yeah.
I see. Got it.
Yeah. And then if you print prim 2, okay, 2006. Now we can check that, right? Go up to line 1 in the previous thing and set premium equal to prem 2, or do that, yeah. Okay, and re-execute it. There you go. One more. All right.
Love it. I love it when things work, Steve. They don't always work.
It's up to you which version you want to use. I don't care.
So, I mean, I am surprised at the leverage here. Can you help me? Should I not be surprised? I mean, you've increased the premium by like what? I mean, what's the percentage increase there? Not much. A fraction.
3%, right?
3% increase, which yields straight through to a 3% increase. Is that 3 percentage point increase in the return on capital? So there's a lot of leverage there. Is that right?
Well, we should know what the yeah, you're writing at 1/3 to 1, right?
Ah, yes.
Because you're 20,000 premium, 44,000. Oh, you're writing it a little less than 1 to 1, right? Because the assets include the capital. Capital is going to be about 24,000.
Yeah, but for $600 more premium on a $20,000, like, I mean, I'm surprised at how fast that moved, right? So like, what's $1 improvement? I guess it's not big of a deal, but no, is that just how it is? Or
well, it's okay, but the capital is about equal to the premium. So it's like 600 over 20 is 3%, and it was 11.8, which is almost 12. 12 plus 3 is 15.
Yeah.
Right?
Okay. Yeah.
So I think it's okay.
Okay. Cool. Boy, 3% rate increase just goes straight to the bottom line. If that's the way you're thinking about it, right?
Although if you re-execute 21, there, we'll see the EPD should have come down a bit, right?
Yeah. Before. Not by much.
Yeah, okay. Didn't come down very much. All right. No,
okay.
not very much.
We'll move on.
All right. Let's carry on, and we'll keep going with the 15% return, right? So this, like, execute this cell here.
So I haven't messed up any variables here, have I?
No, you're fine. We're just going to work to 2664 instead of the other thing. It's fine.
Okay. I see. Yes.
So what this does, this function, calibrate distortions here, it calibrates the distortions, right? So we've got those 6 distortions that I like to use, and they're all single parameter distortions. And what this block is showing is the parameter coefficient second from the end there is those are the coefficients that you need so that distortion with the 99.5% capital will produce the premium that you want, okay? And so you see all the premiums are all, in P column there is all 2664, right? The Q columns are all the same. The CLC is all 15% because that's what we want. And then the parameters are, well, so the constant cost of capital is just assumes all capital earns 15%. So the parameter is 15%, right? That's what you want. pH, remember, that's the one that takes S to the power 0.603, okay? The Wang one does the normal thing, and it's sort of shifting across by half. The dual one's doing 1 minus S to the 2.121. I think previously we looked at dual with a parameter of like 1.9 something. So somewhere around 2, that's a fairly sort of common kind of value. And then the TVaR there, 0.398. That's in a way the most interesting one. That's saying I can price by ignoring the best 39.8% of outcomes and just averaging the worst, what is it? 60% of outcomes. That's how that one's working.
Interesting. I will say, what does pH refer to?
A proportional hazard.
Okay, interesting. Because that's actually I was saying earlier, my stupid pricing, but that's the one I actually used was a fraction of a power.
Yeah, the two. So the Wang transform was obviously introduced by Sean Wang.
Yeah.
But the other one that I think he wrote a paper that might have been published in the proceedings was proportional hazard.
Yeah. Okay.
So that was one of the.
I didn't even know the origins of it. I just loved the single parameter nature of it. I thought that was better.
Yeah. It's all. So this is just doing a little Newton-Raphson to hone in on the parameters. Great. Very, very robust.
Yeah,
okay.
Cool.
It adds to the portfolio object. Has this dictionary, which is then these distortion objects, right? So we can then do things with these down the road. Okay,
cool.
So let's look at these guys. Let's see what they look like. If we execute the next little block of code here, we'll get some pictures of them all. All right. So here, we could probably spend a long time on this. There's a lot of. So this is the first one is constant cost of capital. Let's come back to that one. Let's start with the proportional hazard one, right? So that's. The orange line there is it's S to the power 0.6. So a little bit more than the square root. So it's, it comes in pretty steep at 0. In fact, an infinite slope at 0 and then going up, and it's sort of skewed towards the small s range, right? In a sense. Particularly when you compare it to the next one, the Wang one, that's much more symmetric, right? The left and the right is sort of symmetric. It's a very middle of the road kind of distortion, the Wang distortion there. And then your dual moment one is kind of like if you imagine sort of reflecting in opposite diagonal line that goes from top left to bottom right, it's thicker for larger s and thinner for smaller s, right? It's sort of the opposite of what you've got on the proportional hazard side. I don't know if you can see that, but it's it bulges out in a different way, right?
So this means that for higher probabilities of loss, you have a higher proportional margin.
Yes. So it's right, exactly. So the pH is going to charge relatively like higher markups for bigger losses, whereas your Joule moment is going to be, it'll still charge quite a lot for a big loss, but it'll charge relatively more for less, for smaller losses.
So if but let me think about a concrete example, because like let's say you have a 1% chance of loss catastrophe layer. Right. In the old days, I used to do the point raised to the power of an exponent of 0.6, and you get like a 3.5-ish probably right on line, right? And but if you apply that to like a 60% EL layer, you get a much lower proportional increase, right? Because it's closer to 1, and so you have that, right? And this thing, I don't know what that would be. Maybe we could probably even.
So what this Joule guy, it would basically double the rate. So the slope comes in there at about 2. At the small length. So it's sort of, its maximum multiple would be about 2, right? So a loss ratio of 50%. So it's kind of cheaper than your proportional hazard that might give you a 3x or 4x type of multiple for
it's cheaper on the I mean, we call it lower end, on the lower probabilities. Right?
On the
on the high end covers, on the
high end covers.
Yeah, it's cheaper up there, and then so the intuition here. I mean, I don't know. We can make up intuition or anthropomorphizing this, but something like, I don't believe my data on the low end, and so I'm going to crank the load on the lower end stuff.
Yeah.
Who would use the moment?
Let's just look at the other two, and then we can talk a little. So the tail one you see that's sort of the cheapest it can be. The tail VAR is the cheapest it can be on the left for the large losses, and kind of the most expensive it can be on the right, because you can see after like 0.6, it hits 1, right? I mean, it doesn't get any more expensive than that. It's just like maximal possible expense out there.
Yeah.
And then let's go back to the left-hand end. So the constant cost of capital one, can you scroll a little more? It hasn't come. There we go. Now, this one is weird because all of the other guys are continuous, but this one actually jumps up. So it takes the value 0 at 0, but for any number bigger than that, it's on the sort of the slope line, right? It jumps vertically up at 0 and then goes along. So it's sort of maximally expensive for large losses, and essentially as cheap as it can be for all the other claims. Okay. And I don't know if you remember, but when I introduced these 5 guys, what I said was that they're in order of the sort of most tail-centric, most concerned about tail risk. That's your constant cost of capital. And then your pH, and then your TVaR is, I said it's kind of the most concerned about volatility, because management is often, I'm sure you've met management that is concerned. Particularly, they buy a lot of what they deem to be fairly expensive reinsurance that provides great protection out in the tail, but then they never recover from it, and they have all these attritional cats, and they're like, I'm getting killed on this business, and it's all about the volatility, and I'm missing earnings estimates and all that sort of thing. So they want something that reflects that pain that they feel with higher frequency, lower return period losses. And that's what your TVaR distortion is giving you. It is more volatility-centric, if you will.
So this is like the earnings area, and this is like your capital probabilities.
Yeah, the left-hand side is your capital. The right-hand side is kind of your earnings. Yeah, exactly.
Yeah. I spend a lot of time designing earnings covers for companies.
Yeah.
Cool.
Okay, so those are our 5 guys. Let's now... yes. This next little block, just run this. There's a technical problem with the constant cost of capital distortion that it is not continuous at 0. It jumps up. And that's just awkward to deal with. And so I want to just get rid of that problem by approximating it by something that, rather than jumping up, goes up very, very steeply, but continuously. Okay, so I'm just replacing it by, to the naked eye, it'll look exactly the same. but it is ever so slightly different. And you can see the last row there evaluates the original function and what I've replaced it with at a return period of 10 to the 20 years, right? So I mean, like older than the universe, and you can see the left hand 13%. That's your actual constant cost of capital distortion. It's like saying, I don't care, you got a 10 to the 20 year return period. I'm still charging you 13%, rate online. Whereas the approximation is somewhat more reasonable. It's saying I'll charge you, 1 in 10 million rate online. But it's a technical issue. We don't need to get into that. It doesn't really affect anything other than the ease of calculation.
I would like to kind of just come back to something that's just been hitting my head and thinking about it for the last minute, which is, do companies use I don't have any experience applying any of this stuff, and I think you do. Do they use more than one for different situations? Do you have to kind of pick one as a company to operate with, let's say, for buying reinsurance or other uses? How do they actually, would they use, is one of these like dumb and another one's good? Is that
what? All right. So they imply, as we will see, we're going to get to the allocations that they imply. And we've hopefully I've maybe convinced you that the CLC one is more tail centric and the VAR one is more volatility centric. And so in a way, you're going to try and find the distortion that sort of matches what are your investors concerned about, right? Because what this is really, it's this function is sort of telling you how your investors are pricing the capital that they're giving to you. So in a theoretical world, your investors would sort of have a G. They would have one function like this, and it's up to us to sort of elicit which one it's likely to be. Right. And it tends to be one more to the right-hand end of the spectrum than the left-hand end of the spectrum.
That's amazing. Yeah, because this is the regulatory put, kind of, right? Out here on the left side, like that, like regulators are all worried about solvency, right? And then in an admitted world, they pay the claims out here if it goes out the top, right? So is this an agency cost? Yeah. That's what you're reflecting there.
Let's carry on and come back to that one. Come back to that.
All right.
Section 7. So now we're going to get to allocation. So far, what we've done, let's just recap, right? We've built this portfolio. It's got two lines, cat and non-cat. We've set up, we wanted to price to a 15% return. Thank you for correcting me on that. At a 200-year capital. We've calibrated 5 distortion functions that will produce that pricing in total. And now what we want to do is ask, well, how would we allocate that premium to the two different units? Okay. And this is where having these risk-adjusted probabilities comes into a beautiful thing, right? Because if I've got X is cat plus non-cat, and I'm applying, an expected value operator to it with the risk-adjusted probabilities, well, I can apply it to cat and I can apply it to non-cat, and I get an allocation, and it's additive and it's beautiful. So we can do that. So this function.
Now you just have premium targets. That's what we're going to say.
Now we're going to get premium targets, exactly. Right. So this analyze distortions here, that does that for us. It's going to run all the distortions that are attached to this object. It returns this AD object that has a whole bunch of exhibits. So let's just look at this dual exhibit. So all of the other exhibits there, they're just for different distortions. They all look basically like this. And it's showing, again, the 8 things I think you should look at. So loss ratio, margin, premium, leveraged, capital, ROE, assets. Okay? And you see total ROE 15%. That's what we expected, right? And we see the premium is the 26,664. That's what we expected. And it's telling us that the allocation is cat 3,059, non-cat 17,605. Okay.
And so so this is also for a fixed policy base, right? So we specified in effect the loss producing stochastic process, right? Which is effectively how many policies you get in each. So this is saying once you told me which policies you're going to write, I'm telling you what the total amount of premium should be for all those policies. You can allocate between the policies, and here's the targets. So like maybe 100 policies here and 50 policies here, as long as it all adds up to 3,000, or is that right?
Yes.
3,000? Then we're good. And these ones up 17, we're good. Yeah.
And so what are overall the total loss ratio there is 82.7%, and for non-cat it's 85.1, and for cat it's 669, right? So we got a pretty good spread. We've got an allocation of the capital. I don't think that's necessarily terribly useful.
Q?
That's Q.
Yeah.
And the reason it's not, the reason it's tricky is that, and this is in many ways the most interesting thing that comes out of this analysis. Look at the ROE row, okay? The ROE for cat, 9.2%. The ROE for non-cat, 19.3%.
Yeah.
Overall ROE, 15%. Now,
Well, we should just cut this division and just write this one.
okay, well, yeah. And why is it coming out like that? Because that's probably the opposite of what people would expect, right? You would expect cat should be a higher return. Well, it is a higher margin if you look at your loss ratio, because it's running a 69 instead of an 85. So it's a higher margin, but look at the leverage. It runs at 0.3 to 1, right, the PQ, whereas your non-cat here is running at 1.3 to 1, okay?
Yeah.
And so what's going on here is your cat line has got this big thick tail. And if you sort of think of it in terms of supporting everything with debt rather than equity, where you're more attuned to think, well, yeah, I've got AAA, AA, what have you, you've got this, in a way, a nice long tail on the cat. Is very suitable for turning into debt. In fact, we do, right? We call them cat bonds. There's a lot of them out there. What do we know about cat bonds? They don't make a 15% return because mostly they got a rate online that's like single digit. They make single digit returns. They are a cheaper form of capital for bearing cat risk. And that is reflected in the fact that the ROE for cat here is coming out sub 10, even though it's quote unquote riskier, you can finance it with cheaper capital because, but it's,
so your
higher
cost of
margin,
capital is also low, right? Your hurdle rate is lower.
Your hurdle rate is low.
Right.
And then the non-cat, the tail falls off very quickly. So you can't really, it's all equity, right?
Yeah.
You or sort of like equity-like, very risky, very high, it would be like mezzanine or worse debt, okay? It's more expensive. But you need much less of it because you can write it at 1.3 to 1.
So this analysis is really about saying what is good or bad here, like what's my cost of capital? Because you're saying your weighted average cost of capital, whatever you want to, whatever heuristic you want, or methodology you want to use there, is saying what you need is this, given the mix of capital you're going to have. And so more isn't always just better. You want to only you want to deliver the return your investors are requiring. And not really much more, because then you're leaving some money on the table. You could be getting more capital if you could deliver only what they want, right?
Right, and the key, so the big paradigm shift here is we've moved away from the sort of constant cost of capital, economic value added view of the world, which assumes that all capital has the same price.
Yeah, cool.
And it doesn't, right? You know that because you know your AAA bonds have a lower return than your, AA and so forth. You've got this tranching of capital according to how exposed to loss it is. And so just knowing the return on a business isn't so useful to you anymore. You can't do what you just said. It's like, oh, I'm going to can cat and then I make a 19%. You can do that, but the guys who provide the capital, they want a higher return for that business.
Your cost will go up. Probably
your cost
faster.
will go up. Yeah.
Yes.
Yeah.
Which is not recorded here or represented here necessarily, right? Because you've given it as an input.
Yeah.
Okay.
So this is the big change with this mentality, right? That cat is expensive from a margin perspective, but cheaper from a return perspective, and you reconcile the two through the leverage.
Yeah. Boy, that's cool. Now, one thing that I observe out there in the market these days is repricing going on in certain areas where capital, so you might have, let's say, another portfolio. Let's put another portfolio in here. I'm not saying we actually do that right now, and we call it California wildfire, right? And we say everybody's freaking out about our ability to measure. I don't know how you want to. You could probably equivalently formulate the problem in different perspectives, but the capital's more costly there now. Do you have to have, again, as a question I asked earlier, maybe you can keep punting it for me, that's fine, but can I put a different distortion function on different portfolios and then add them up again? Or do I have to represent it differently in kind of the expected loss somehow?
So the idea here is that the G prices all the capital the investors don't really care about the components. They just care about the total that you bring to them.
Okay.
I think there's a slightly different dynamic going on with the repricing, which is that they're not off on the profit piece. They're off on the expected loss piece, right? It's repricing because they got the expected losses wrong.
Yep.
We're kind of cheating here in a way. We're assuming that we've got a reasonable stochastic model of the losses, and so the loss estimates are, they're an unbiased best estimate of our true expected outcome. So that sort of repricing is more an effect of oh no, my ELs are wrong, than oh no, my cost of capital is different than what I thought. Now, I think it's related, right? Because investors lose faith in you as management if you can't price the business, because that's the only thing they pay you to do, basically, is price the business. And so it's a really bad day for management when they have to face up to the fact that they've been mispricing this business for a while, and that could probably lead to higher cost of capital for you because investors have lost faith in you. And this is why management is so concerned about having losses above plan, is because it's hard to distinguish, was that bad luck, a bad roll of the dice, right? We just had a bad, or is it something more systematic, like maybe we've seen in cat, and particularly in the sort of non-model cats over the last few years.
Yeah. Okay, we could talk about that for a while. I will stop.
We could. Yep. All right. So that was looking at for one distortion, right? That was looking at it for the dual distortion. And if you so all the stuff that's going on here is I'm just pulling out from the answer that we computed with the analyzed distortions. I'm pulling out the loss ratio and the premium across all the methods. Okay, so the code doesn't, you can look at the code, but we're more interested in looking at the answers here. So we got the methods. The ones that are called dist are our distortion spectral risk measure methods. Okay, and they're sorted from the highest premium given to cat to the lowest premium allocated to cat. And so you see the distortions fall in the order that I said they would fall, right? Constant cost of capital, most expensive for cat, and then you've got your pH in the middle, and then you've got your Wang, Joule, TVaR. Okay.
Did you specify all of these, or did they just say give me everything out of the box?
I specified. Okay, so we told it to calibrate those 5 distortions. So remember, way back we did our calibrate distortions to our 99.5 capital.
That was this. It took a very long time to run.
It took 13 seconds to run, right? That's a lot of heavy lifting goes on that.
Yeah.
Okay. Now it also, so the other things you've got in here, you've got things like scaled EPD, equal risk, scaled VAR, TVaR. These are what I politely call the BS pricing methods, right? Which you can interpret how you choose. They're sort of no real theoretical basis exactly, but they're commonly used things, and they're all also described in the book. Co-TVaR is the, allocating capital. Okay, so here's the characteristic of all the BS methods. They all work as follows. They allocate capital, they apply a constant cost of capital to it, so they ignore the fact that we manifestly have tranche cost of capital. They just say all the capital costs 15%, and they add the loss cost, right? That's how they all work. So they're all just different ways of allocating capital. Probably everybody knows about co-TVaR, where you allocate based on the tail events. And so there's no surprise that co-TVaR is up there at the top. It's tail-centric. And in fact, almost all the BS methods, they're all tail-centric, right? Compared to the sort of, the Wang is our middle-of-the-road distortion, is the third from the bottom. The bottom one, EL, that just prices based on expected loss with an average, same margin for everybody, right? So that's not really a price. That doesn't look at risk at all. It's just grossing up for...
Same dollar margin or percent margin?
Same percentage margin. Okay. So everything's priced to an 82.7 combined. Right? You see? Yeah. Right. Okay. So you sort of take that one off the table. That's not risk sensitive.
It's only how you price the vast majority of all insurance business.
Well, yeah, but for the vast majority of business, the risk doesn't really matter.
It's out of scope. Yeah, I agree. I just thought I'd just make that little thing.
We're really focused here on cat. This is all about cat.
Yep.
So you get, so there's a few things to note here. One is your constant cost of capital distortion there would have you writing non-cat at 112 combined, which nobody likes that, for good reason. You don't want to get into writing business necessarily below cost.
Bang, right there. Yeah, got it.
Yeah. But there's clearly something going on here, right?
Wow, because you're making so much money here. Well, you can write this at a negative margin.
You've got such a lot of expense there, and it's what's going on is in the bad outcomes, the non-cat lines kind of contribute assets to pay cat claims. Because when you have a really bad outcome in this portfolio, what it will consist of is a really bad cat loss and an average non-cat loss. That's just what it will be. And I can demonstrate that to you in different ways. But that's
diversifying.
What it will be.
It's diversifying.
And so what that means is, any assets that you get from the non-cat line, you're going to have, because you have sort of, it might even be like a little bit less than average. Those assets are available to pay claims on the cat side. So it's kind of functioning like financing in the worst states.
So it's like, there's a term which is usually used as a pejorative term, the diversification, right? So you're saying I'm going to write negative margin business somewhere else in the world in order to offset my Florida wind exposure. The BS method, it's not like we're being super kind to it here, but there is some construct in which that can make sense. If you're if you're writing the Florida stuff for this kind of loss ratio, diversification ain't so bad because at least gives you some assets to throw out to Florida. I don't want to over-rotate on the 112. There's sort of some other assumptions that go into that. But throw out the top two lines, right? Fair.
You've still got a very wide range of premiums indicated for the cat line between 5,200 down to 2,800, right? So there is a massive disagreement here between these methods. Between some of them are reasonable methods. None of them are, I guess, are materially they're all in the literature. Let's put it like that, right? All these methods in the literature, very big difference between them.
Yeah.
So
amazing.
Let's just keep on looking. We've got a couple more statistics that we want to look at. So we've looked at loss ratio and premium. The next block is going to look at ROE and capital. So if we execute this, and again, it's just pulling off the calculations that we've done before, and it's going to put them in the same order for us. Okay. So now what we see is that there's a few things. Remember what I said, all the BS methods assume a constant cost of capital for everything. So that's why there's all these 15s here, right? All of these non-distortion methods, they assume both lines have to make a 15% return. Even though we all know you could finance your cat with cat bonds that never is going to make a 15% return, right? Yeah. So, but the distortion methods don't. The distortion methods think and they look about, where is that capital in the tower? What's the likely cost of it going to be? And you get the differentiation in return for the two different units. And it's not necessarily what you would expect, right? It's the cat line, lower return, but much higher margin, lower loss ratio, lower leverage. Okay?
Okay. And this is the lower return right, part, and then the higher loss ratio, or the higher loss ratio.
Yeah.
Okay.
And then, the capital allocation we can come in. So let's look at the leverage, and this is the asset allocation. That's maybe not so absolutely fascinating. And let's look at the margin in the EL. I'm not sure if there's any messages there, but I think
there's a difference between them, right? Or
this is
not quite that, but yeah.
All right, so let's what I want to get to now is, and where people are going to use this is, well, let's apply some reinsurance, right? And let's see how much money we might have to spend on it. So I want to calibrate. I don't want to waste time on this. I'm going to calibrate some per occurrence reinsurance that buys you from the 80th to the 98th percentile. It works out to be 14.6x of 2.2, and then we make a new portfolio where we apply. So the new line is line 4 there, where you've got the occurrence net of the relimit excess the reattachment. Okay, so this will make a net portfolio for us. If we execute this, it fails validation because there's reinsurance, right? I haven't that's a coding error. I've addressed that for the aggregates, but not the portfolios. So we don't expect this to pass validate. We know it's fine because we've calibrated the gross portfolio. So now what we can do is we're sort of imagining that these distortions there's a capital market, and the distortions price how capital market players charge for their capital, right? So they don't care whether it's gross or net. You'll just need a different amount of capital.
Yeah.
So let's use the same distortions that we calibrated on the gross book. Let's apply those to the net book and see what we get. Okay. So this is what we're getting here.
And so the reinsurance? Did we price it up here?
No, we didn't price it, because what we're trying to do is we're trying to figure out how much we would have to spend on it because of the change in our cost of net capital, right?
Okay.
So we buy the reinsurance. We need less capital because our 1 in 200 PML is going to come down, right? And there will be a change in the cost on the distortion methods. So if we take the difference between the gross cost and the net cost, that will give us the most we can rationally spend on the reinsurance. That's what we're trying to compute. Okay?
Sure. Great. That's awesome.
All right. So what you see here is this is now the pricing on the net book, right? So you see the total column on the right. For all the BS methods, it's all the same. Because for those methods, the impact of the reinsurance is simply I need less capital, but it's the same cost, okay? And then there's a loss cost component as well. And there's a reconciliation later on that will tie back to those two things. So you're just saying on a net basis, you've got less EL, less capital, same cost of capital, gives you a total premium, and it's 18,923, okay? And that's why those numbers are all the same.
And these are bigger here, Wang?
Now, yeah, so the distortions, though, they look at it differently. They say, all right, you need less capital, but you're getting rid of cheap capital at the top, and you're probably going to need more, the sort of relatively more volatility capital is going to be required. So their price is not going to be the same. It's going to vary, and it's going to vary by distortion. And that's what you're seeing, right? So, and you're seeing that the more volatility centric you are, in fact, the more expensive the total premium is going to be, because by getting rid of the tail, if you're concerned more with volatility than tail, you give less credit for getting rid of tail, right? So that you have a higher net premium that you still need to fund.
So there's a kind of subsidy being applied. I'm having trouble with the intuition here. Like the amount of risk has gone down. Like the total, like the
the premium didn't go up. It was 2664 before. These are all much lower than the total before.
Oh, right.
It was 2664 before. Yeah.
Got it.
It's just a matter of how much lower are they?
Yes.
They vary in how much lower.
Gotcha. Good.
And they vary where the more tail centric, the more credit you give for the reinsurance. And this, I'm sure you've been in these analyses, right? You go in and people are like, well, all of these methods, they only care about the tail, and so they would only have me buy cat reinsurance. They don't care about any other volatility, and people don't like that. Well, this is kind of why. It's because if you do something where you say all your capital is the same cost, then yeah, that's the conclusion you're going to be led to.
Yeah, and I do want to make the point here that this is so cool because, I mean, most of the time you make the decision of whether to buy. The analysis either is I'm forced to buy something, so I'm going to try and get the best price. In which case, your own internal analysis of the price is irrelevant because you have to buy it, or you ask the question: am I going to make money on this reinsurance? Like, is the loss ratio over 100? In which case, you'll if you convince yourself to buy it. That's what your internal you want your reinsurance broker actuary to talk you into why you're going to make money on this deal. This is a way of actually quantifying the benefit of capital relief, which has been a pretty squishy thing. And I mean, I was never able to. You talk about it, but then nobody has any framework in which to, evaluate that.
Yes.
Now we do.
Exactly. All right. Let's just wing through the next. See if there's any. Yeah. Okay. So this is your ROEs on a net basis. So if you can you scroll down? There we go. And then I get somewhere we get the differences in the premium, I think. So I don't know that the next couple of things are that interesting. Let's go down to the difference in the premium. Impact of premium by unit. Yeah, the next block.
This one here?
Keep going. Keep going.
This guy.
Well, yeah.
Oop, do you want to go back here?
Okay. So yeah, let's leave it this. This is looking at the difference in loss ratio gross to net. Okay, and so you expect that your loss ratios are going to go up, right? Because your risk has gone down. So there's a couple of things we see here. One is by buying cat reinsurance, this model is saying that there's an impact on non-cat, which that probably has people scratching their heads a little bit. It's like, well, that doesn't make why is that happening? Okay, and it's not just the distortion methods. All the methods do that. Okay, and the reason for that is that by buying reinsurance, you make the cat line less risky. Well, the flip side of looking at that is you make the non-cat line appear relatively more risky, right? So you would expect that it should become slightly more expensive. The other thing that happens is the quality of the coverage that you provide to the non-cat people goes up because they are less likely, you're less likely to have an insolvency that's driven by cat because you've bought cat reinsurance. So they have got a higher quality product, and so they should pay slightly more for it, right? So there's an interesting sort of dynamic there that by buying cat reinsurance, you actually change the product for the non-cat people as well. And you change sort of how you think about their relative riskiness.
What's most interesting to me about this is not monotonic. So we had organized these earlier, right, in a particular ordering. And this seems to be delivering a result which is according to a different ordering.
Yes. So if you look at the premium for cat difference, right, that's pretty close to monotonic. Certainly, right, because that's saying that's sort of the picking up the tail cost of cat, and it decreases as we go down. The thing that's a bit harder to get your head around is what the net impact is on the non-cat line. And that's what you can see. That's where the numbers bounce around.
It's all over the place. Yeah.
Yeah, it's all over the place. It's a bit. You just have to run the numbers and see what happens.
And even the relationship between, these two numbers also all over the place.
Yeah,
like the ratio of these or something like that is also.
Yeah, I'm not sure that you would, find anything there that's going to be particularly helpful.
Super interesting. Okay.
Yep.
What's this?
This is just going to be the same.
Nope, didn't define FF.
Well, that's it. Where did FF get defined? I took F. Just take out the last bit, that. Yeah, take that out and take the comma out. Yeah, there we go. That's just looking at the difference in premiums between net and gross. Okay, and so the total is. So from a corporate perspective, that would sort of give you your budget for reinsurance.
Right, yes.
Right? My cost of capital has gone down by this much. That's the most I can spend. But the sort of weird thing is you get this dynamic that the cat unit on its own would look at the cat column, but they wouldn't see the impact on non-cat. And so you can see that in some of these methods, for example, in a lot of them, the impact is that the non-cat premium needs to go up. Well, good luck telling the guy running the non-cat unit that his premium needs to go up because you're buying reinsurance. So that's probably not going to happen in the running. But from a sort of macroeconomic perspective, it does make sense to think like that.
Yeah, amazing. And so this
and in fact, what would actually happen here is you never start with a gross book, right, and then convert it to a net book. You actually run the net book, and the premium that the non-cat policyholders will pay will reflect the fact that they know you buy cat reinsurance, right? They would be less willing to buy from you if you didn't buy the cat reinsurance. So it's sort of this premium delta is kind of already baked in, and it would be better to think about it the other way. That if you went from net to gross, all your cat books, all your non-cat policyholders would suddenly say, "Wait a minute, you can imagine writing D&O." You drop your cat program, maybe your rating goes down from A to A minus, and you're not even on their approved list anymore, right? So it's sort of more that dynamic than then they would actually see a premium increase. It's already reflected in their premium that you buy the cat reinsurance.
Yeah, your overall solvency is improved by buying cat reinsurance, and so your non-cat policies are more attractive. Okay. Yeah, I'm still kind of working through this concept of the premium allocation to the non-cat line is larger dollars with cat reinsurance than the premium allocation is with non-cat. Am I phrasing that properly? What I'm saying here, right?
Yeah. Mm-hmm.
Right.
So here's one reason, right, why that would be the case is if you looked at the expected policyholder deficit, it will have gone down.
Yeah.
And so the actual expected loss recoveries that the non-cat line will get will have gone up. They will be buying a higher quality product from you than they would have done it without the reinsurance, and a higher quality product comes at higher cost. So the premium needs to go up.
Yeah. The premium, the dollars are so these dollars are going down, right? So let me just get arithmetic here, right? This plus this equals this, right?
Yes.
So they can charge so this is
so from the corporation's perspective, the corporation is going to, by buying reinsurance, its cost of capital goes down by 1033.
Yeah.
But the allocation is that they would give like a 1,200 credit to the cat people, but they would expect 200 more from the non-cat people. But again, think of it from starting from, it's probably better to think of it as starting from net and going to gross, right? Where
if you flip
the
them.
signs would be reversed.
Right. So that's another point of saying like your allocation, because I was thinking about that too. There's like the cat reinsurance cost allocation problem, right? Which you'll have sat in rooms, people trying to figure this out, and very frustrating. So if you went net to gross, the signs are all flipped. So now it's saying the cat team, the cat division manager, you have to pay us $1,200.
Yes.
In order to, that's your allocation of the reinsurance. The non-cat division manager, here's $200 back.
Yes.
Right.
Because all your policyholders are going to run away, so you're going to need to give them a lower premium to keep them.
So in some sense, they're paying them.
Yeah, exactly.
A little bit.
That is part of what's going on. Yes.
Yes. Oh, that's cool. Okay, good.
Yeah.
I'm going to move on because I think I understand it now. So.
Okay. All right. This is just a data frame. If you just execute this, it makes a little exit.
FF.
The FF. Delete the FF again.
Where is it?
On 24, row 24. Yep. Delete that guy and just boom. Okay. So this is just a reconciliation of the premium difference that we saw for all the BS methods, which I said was driven solely by less assets, constant cost, and the difference in the EL. So I just go gross assets, net assets, savings in assets is 9053 times the discount factor gives you 1181. The savings in the losses is 643. You discount that as well, and you get your 1741 change in the premium, which was the number we saw up above.
This up here. Oh, that's
hopefully that's out there somewhere.
Yeah. According to, okay, let's do this. I'm going to spend a second. I know we're going to end before section 8. Is that the idea? Right.
Yes.
I want to spend a minute talking just generally about just sort of how you pick which of these you want, if we can. But let's talk through these, or you tell me, how do you want to?
Yeah, this just models out the distribution of ceded losses, if you wanted to look at that. So it figures out the session to this program has got an expected loss of 665.
Yeah. And
so then you can compare that to the premium that you've got, and you can come up with walk-away loss ratios, right? If the loss ratio is above such and such, it's a good buy, and otherwise it's not.
Or maybe for internal reinsurance purposes.
Yeah, that's all we're doing now.
Okay. And then this is the same.
But quite a range, right? Sort of 40 up to almost 70%. So quite a range.
Wow. Yeah. And only the cat.
And so that evaluation is the corporate perspective, looking at the benefit across the book. This the lower one is the business unit's evaluation, where they feel like they've got more money to spend on the reinsurance because they're not allowing for the offset for the other line that we discussed before.
Okay, so we'll say this one more time, and you're okay to stay on for a few more minutes?
Yeah.
Steve?
Yep.
Yeah, okay, good. So risk visualization, you're going to record some videos that are going to
Yes.
kind of walk through the rest of this book. So there's
Yep.
two topics that I wanted to, so one of them I want to talk a little about these distortion functions, or rather the allocation functions. The concept of the efficient allocation, is that what it was called in the book? Where, how do you disaggregate this? There's a methodology you used. I should have checked this before, but how do we actually take this thing? Where are they? Where's our orange? Where's our lines here? These things, and then disaggregate that into the different portfolios. How does that work?
Okay, so that's what we've been doing down here, and
Yeah.
it works by you make your column. You know, if you're in a spreadsheet, right? You've got a spreadsheet, and it's got rows of your simulations, and line 1 or unit 1, unit 2 total, and then you've got your objective probabilities, and then you've got your risk-adjusted probabilities, and you're doing the sum products of the risk-adjusted probabilities
Okay.
with the unit losses. So that's all that's going on here behind the scenes.
Okay.
That's-
okay. Good.
yeah.
Some product of risk-adjusted probabilities. Okay.
So
good,
and
thank
it's
you.
it's the GPs that we computed in the first section. So you go your objective probabilities, you decumulate them to get your survivals, you apply
Yes.
G to the survivals, and you difference it. So it's like a 4-step process, and that
And it's-
gives you your.
Isn't it amazing how much easier it is to work in discrete terms than continuous?
Oh yes.
It's so much more intuitive. Now, the last thing I want to talk about is how do you pick which one of these you like?
Okay, so there's a few things to look at, right? One is the types of things we were just doing, right? Management typically has a view around how they feel about various forms of reinsurance and how they feel about tail risk. And what we've seen is the ones to the right, the dual, the TVaR, they're often more in agreement with how management's thinking. Certainly the ones on the extreme left are they get dinged for all you care about is tail loss. Right?
Yep.
And that's not how management thinks. So the ones to the right are more consistent with how management's thinking. Then you can also, there's various other things you can look at here in terms of implied minimum rates online, implied sort of, how when you adjust the probabilities, what's the ratio of the adjusted probability to the objective probability? Is it 5 to 1, 10 to 1, 50 to 1, or does it cap out? And the ones on the right, they tend to have a maximum cap, right? So maybe that dual one will double the very small probabilities. They'll get doubled. Whereas the proportional hazard will multiply them by 5, 10, 50, 100, right? They'll get, so you get this greater sensitivity on individual very large losses. And that's generally not people don't like that. And then you can look across, we just had 2 units here, but you could have 10 units or 20 units or however many units you plan with. You can look at the implied allocations for those as well and see, these appear to be sort of reasonable. But there's unfortunately, we can't, I can't prove that any one of these
No, of course
is
not,
better
right?
than others, but,
Yes.
but some of them, they sort of pass the smell test better than others.
So like you have a giant list here. So I'm thinking like some point, Steve, the vision, the hope, the dream here is for enterprising bunch of actuaries to pick this thing up, right? And then they'll show up in management's boardroom and say, well, hey, we got 15 different allocation formulas. Let's sit down and roll up our sleeves and pick the one we like, right? Or you tell me which one you like, and then I will give you all these great things that you want. All right? Is there any advice? Just advice for somebody who wants to do that, talk to a non-practitioner about the consequences for picking these and how, what are the intuitive decision kind of points that would help a CEO think through this with the help of, one of these brilliant actuaries that are the fans of the Not Unreasonable podcast.
Yeah, so it's the degree to which they kind of overweight the extreme outcomes. Is it capped, or how big does it get, right? And that sort of skews you. And then I'm a big fan of the sort of proof of the pudding's in the eating. Apply it to your actual data, see what it says, which of those sort of implied set of results, which then have implied strategic actions, right?
Yeah, right, exactly.
If you're saying, this does not value this reinsurance so highly, but it values this other reinsurance, it's going to shift what you buy. Is that consistent with what management has sort of always felt, or it might be what management actually does, because they maybe ignore the tail-centric methods, right? They don't like them anyway, and they're like, yes, at last you're telling me something that's actually consistent with how I feel about things. So it's very much a dialogue, though, and keep it around results for units. Keep it very tangible, I think, is a good recommendation.
And so one area here would be, we're talking about reinsurance pricing, I guess. I don't know if that's going to be an important consequence here of these assumptions, is how you price reinsurance, and so the implications of reinsurance pricing. I mean, the amazing thing about this whole package, of course, is that it's very cheap in terms of time. You specify your distributions, you do all the hard work first, and then you can run this notebook. I'll tell you what I would do, Steve, if I had to get my hands on this thing 15 years ago when I first started doing this. I would copy this notebook. I would put in the distributions of the things that I know, and I would just run it. And I wouldn't, the work is already done. I mean, it's
exactly
amazing.
Yeah.
Okay. Any closing comments, Steve?
Please look out. So as David said, we'll put some links to other videos. If we've gone through a lot of things here very quickly and at a high level, I've got a number of sort of 5 to 10 minute more digestible videos that cover specific topics on using aggregate. If you have any questions, my email is in there. I think I set up help@aggregate.capital as an email address for this. I'm keen to get people using it. This is all free. I think it's very useful, and good luck. Let me know if you find it useful.
Yeah, absolutely wonderful. I've so enjoyed this, Steve. Look forward to continuing our collaboration on the Not Unreasonable podcast. Might just be a you and me show eventually. But my guest for this 7th time, I think, or something like that, is Steve Mildenhall. Steve, thank you so much for all your work here and for joining us today.
Thank you.